In this video, I will compare the insertion process for a maximum heap, a minimum heap, and a binary tree. For the maximum heap, this is what we learned prior to exam 1. In that process, we start out with 18 and then 21. Remember, the heapification rules require that the larger values need to be heaped up. So this became 21 and 18. For a complete binary tree, we fill in the next element. So this becomes 7, and then 34 ends up here. So again, we move all these elements. This becomes 34 at the top, then this becomes 21, and this becomes 18. We now put in 19, which goes here. Next, we are going to put in 6. 6 will go here, and then 22, which is next, initially goes here. But we heapify it up, and now 22 is here, and 7 is there. Next, we are going to insert 3 and 2, which are both here and here. They are both less than 18, so they stay in the tree. So this is the tree that's initially presented in the first portion of the image as the maximum heap. The minimum heap is the exact opposite of the maximum heap in that the smallest values are higher in the heap and the lower values are lower. But it has the same property as the maximum heap in that there's no actual sorting, just only the top element will be smallest. So first we have 18, and again we have 21. 21 is larger than 18, so it stays lower in the heap. 7 is put here. Now 7 is less than 18, so we heapify and put 7 at the top. Next we put in 34. 34 should be at the bottom. 19 goes here. 19 is less than 21, so we swap those. Next we're going to put in 6. 6 would initially go here, and it's going to move all the way to the top. So what's going to happen is 18 is going to swap with 6 there, and then 7 and 6 are going to swap, so therefore 6 is now going to be at the top. 22 will initially go here, and it is less than 7. Now we put 3 down here, so 3 is going to go all the way up. So it turns out all of these are going to be switched. So 3 is up here, we're going to have 6, we're going to have 19, and we're going to have 34. Then we are going to put in 2. 2 goes here. So then this comes up. So this should be 19. So then we'll have 2, 3, and 6. And so here is our minimum heap as presented in the image. We see that every element is smaller than the elements below it. For the binary tree, we insert them as a way to be able to search. So here's the idea. We would create a node with the piece of data 18. Then we would go to the right because 21 is larger than 18, and we would make that what is known as its right child. 7 is less than 18, so 7 would go here. 34 is greater than 18 and greater than 21, so it goes here. 19 is greater than 18 but less than 21, so it's going to end up here. 6 is less than 18 and less than 7. 22 is greater than 18, greater than 21, and less than 34, so 22 goes here. Then we have 3, and then we have 2 as the last two elements. One thing I want you to take away is that we have this worst case scenario here. This portion of the tree is essentially a glorified linked list. So when we study trees, we're going to say that we want to obtain big O log of n search time. We're going to learn several trees such as AVL trees, B trees, red-black trees, and splay trees that perform balancing in order to be able to perform this task. But those can be complex. The reason why we can get a benefit from, say, a maximum heap, when we have 34, we know that 34 is always going to be the largest. And then all we need to do is ensure that we maintain this complete tree property. We see here that those elements are the maximum values in terms of where they can go, because as they are a dynamic array and the ordering is 34, 21, 22, 18, 19, 6, 7, 3, and 2. So we don't have any empty spots, which makes it a complete tree. Therefore, when I want to remove 34, what I need to do is I move 2 here up to the top, as we've learned before, and then all I need to do, since it's complete, is just grab the larger value and continue to sort down. So it's going to be 22 will be moved up here, and then we would move 7 up, and then 2 would be moved down here. So we only are dealing with these elements. We don't have a potential worst case scenario. We're going to see in the write-up that this is where we gain this K value.